So far what we have done is we derived few relations to understand or analyze rotational motion of an object or a system of particles, and I have just summarized these results on this side, right? And the main important results that we have derived or which are of use are we have described two quantities, vector quantities, angular momentum and torque, which are given as cross product of two other physical quantities, the position vector and momentum. We also discussed special cases for these quantities described as fixed axis rotation, and under that what we realized is we are only interested in one component of this angular momentum or torque, and which we can take along the z direction. So we can write down these components Lz and tau z, and then the relation becomes a bit more simplified in the sense that we can write down the z component of angular momentum in case of fixed axis rotation as I omega, where I is the moment of inertia, and similarly we can write down the z component of torque as I alpha, where then I is again the moment of inertia and alpha is the angular acceleration. And by analogy, we also wrote down the rotational kinetic energy or the kinetic energy of rotation, and that is equal to half I omega square, right? So in writing it this way, what we have done is basically we have defined a quantity, the moment of inertia, which is then given as the integral of dmr square, as a mass equivalent in case of rotational motion, right? Okay, and now what we are going to do is we will see a couple of examples where we can use these equations to understand their application in actual systems, right? Okay, so the first example that I am going to take is of a massive pulley. Right. So as the figure shows, this is my simple system. I have two masses m1 and m2 connected by a string, and the string is still massless. They go over a pulley, right? And the pulley helps in transferring the tension so that the motion of these two masses is coupled. Now we have done this problem earlier. Okay? Now rather than saying that the masses are connected by a massless string going over a massless pulley, right? Now we are saying that the pulley has a mass mp, and that means now the pulley is free to rotate and will consume energy, right, in that rotation. Right? So now the system is slightly different, and that way the motion of the system or the evolution of the system will also change, and we have to look for the new equation of motion for all the participants of this problem. Okay, so as we usually do, we can start by writing down all the forces, and now in this case the torques acting on this on the system, and then look at their relation and then find out the subsequent motion. Okay. So let's do that. So for the masses, for the falling masses, we'll have the force of gravity always acting downwards. We'll have the tension in this string, right? However, now since the pulley is massless, one cannot actually say that the tension on both sides of the string has to be same, right? The pulley can now balance two different tensions on two different sides. So we'll put it as now T1 and T2. It becomes more general, right? So these are the forces on this thing, and then under these forces, the masses are going to have a motion. So let's write down the accelerations as A1 and A2 as the direction shows. So then now that becomes our convention. Okay. So A1 going down is positive, A2 going up is positive. So I have set a particular convention as an orientation for the system to move. Similarly, now we also have to worry about the pulley. So we'll write down the forces acting on the pulley, and as the moving masses, there is a gravitational force acting on the pulley, pulling it downwards. Now, of course, the pulley is fixed, so the pulley is not making any translational motion vertically. So there must be a normal reaction which is provided to this pulley, and which will be provided by the hinge or the pivot point which is supporting it, as well as the pulley also feels this tension T1 and T2, however in the opposite direction. Right? Okay, so this is then my system, and now what I can do is I can simply write down the equation of motion for this, and okay, and another thing that we have to add here is that my pulley is actually undergoing rotation. So since the system is moving in this particular way, this is my rotation direction. Okay, and let's say it rotates with an angular acceleration of alpha, right? Because it's under forces. Okay. Okay, so now we can write down the equation of motion. So let's start writing it down. For mass 1, we can write down. So I'll say equation of motion, and first translational. So F equal to ma type. So T1 minus M1G is equal to M1A. Oh, sorry. M1G minus T1 is equal to M1A, right? And M1A1 actually. So because since we have set the convention this way, then M1G is actually in the positive direction, in the positive sense, right? Similarly, so this is equation 1. Similarly for mass 2, now we have the acceleration going the other way around. So T2 minus M2G is equal to M2A2. So this is my equation 2. Okay. For the pulley is not making any motion in the vertical direction. So for the pulley, it's basically, well, now actually the sign will not matter. But anyway, let me take N as my direction, positive direction. So N minus T1 minus T2 minus MPG, because all of them are acting opposite to the normal reaction. So this is for the pulley, and of course this, I mean, we'll see that if you start solving for acceleration A1 and A2, then this equation is actually a redundant equation, because there is no motion involved there, right? So it just balances all these 4 quantities. Anyway, so these are the 3 equations of motion related to translation, and now we will have an extra set of equations. So equation of motion for this system, considering the rotation of this pulley, right? And what is the equation of motion? So since the pulley is undergoing rotational acceleration, it will have a torque acting on it, which is then, since now this is a case of fixed axis rotation as far as the pulley is concerned, so tau is equal to I alpha, and we can also so this is not actually mentioned in the problem, but what is given is this is also the center of mass of the pulley. So the axis is passing through, is perpendicular to the pulley, which could be taken as a disc, and passing through the center of mass of the pulley, of the disc, right? So tau is I alpha, where then we know what is the value of I and alpha, and this is equal to the torque applied on the pulley. So let us say if the pulley has a radius r, right, then about the center of mass there are 2 forces acting on it, and they both will give us opposite sense of rotation. So we will get T1r, that's the torque, so force and perpendicular distance, T1r minus T2r, right? So this is equal to I alpha. So now we have these 4 equations which correspond to the equation of motion of these 3 particles, right? Okay, and now we have to look for, now the system is not yet fully defined, because what we have is we have 2 unknown tensions T1 and T2, we have 2 accelerations A1 and A2, right? And then we have this angular acceleration alpha, right? So we have 5 unknown quantities, and we only have right now, well, 4 equations. Actually rather not 4 equations, because this one is okay. Anyway, so we have 4 equations. We need another equation to solve this, and that will come from the additional knowledge that must be provided in the system. So let us say this rotates, the pulley rotates, right? Or the masses move without slipping. So basically what that means is whatever motion this rope makes over this pulley is also leading to equivalent rotation of the pulley, and if that is the case, then for motion without slipping, we have another condition which basically will then say A1 in this case is equal to alpha r. Okay. So because the acceleration of this mass, right, is then simply going to be equal to the total the rotation in this one, right? Okay, now one thing that we can still simplify in this entire scheme is that because we still don't have all the parameters, if we take this as A1, this as A2, T1, T2 and then alpha, we still have only 4 equations, because as I said, this one is a redundant equation. It is not going to solve the problem, right? Or it is not going to give us any new information from here, right? Okay, so the extra information that we can now see in the system, right, which to begin with we use the general term, right? How we are looking at the system, we can always find relations between these two, is that since the two masses are actually connected by the same string, right, then motion of this mass has to be equal to, the acceleration of this mass has to be equal to acceleration of this mass, and that way we'll also have A1 equal to A2, right? So then these are the equations. So then, and once we have A1 equal to A2, so basically we have reduced one variable from the equation. We have 4 unknowns, we have 4 independent equations to find out these values. And now what we can do is, we can solve for this A1 or A, now we'll call it as A, right? So using this, you can solve for it, and the result should do this, use these 4 equations to solve for A, and the result comes out to be this, m1 minus m2 g over m1 plus m2, so total mass of the two systems, plus some additional mass mp over 2. So this is the acceleration of the two masses, which comes from, because so then the extra term mp by 2. So we could have done this problem with taking a massless pulley. You have done this previously. If not, then just go back and do it once with massless pulley and now with the massive pulley, and we'll see the effect of mass of the pulley on the two accelerations. Okay. So this is one problem. We can take another one which is similar to this. Let me wipe it out here. And now we can take another example. Example 2. And this is, basically this is rolling cylinder on an incline. So the cylinder is rolling down an incline, or an incline with rope winding and pulling a mass m. Right. So this is my problem, and if we see the figure, then it will be more clear. Basically what we have is, we have an inclined surface. Right. So let us say theta is the angle of the incline. Okay. I have a cylinder here whose axis is again normal to the board. So I have a massive cylinder here. Let's say its mass is m1, right, and its radius I can take as r. Okay. Okay. And now what we have is, we have a rope going over this. So the rope is then connected to a massless pulley in this case, and there's a mass, let's call it m2, attached to this one, right? And now the cylinder rolls down. So the cylinder basically rolls down. So let's call this as A1. The cylinder rolls down the incline. It could roll up also, depends on M1 and M2. But anyway, it rolls down the incline, and by doing it, it winds the rope about on its surface, right, and thereby pulling the mass m2 up. So let's take this as A2, right, and since the rope goes about, and the rope is massless and all that, right? So this is my system, and again we have to find out what is A1, A2 and other things. So let's again the same way, we have done this inclined problem earlier. But in this case again we have to worry about the rotation. So let us see what are the forces acting on it, right? So on this one, about the center of mass, M1G acts downwards. Then we will have the surface normal, so normal reaction. We can make the problem or solve the problem for a more general case by considering that there is a friction about in the surface and the cylinder, and in fact for any rotation there has to be friction between the surface and the object. So there is a friction. There is also tension T in the spring, which is holding mass M2. Similarly, for mass M2, we have M2G and tension T, right? And now in this case, since this pulley over which the rope is going is a massless pulley, these two tensions are exactly the same, right? So T and T. And now, well, there is nothing else on this other mass, right? Okay. And let's take again, this is my direction. So what I can do is, I can break this mg into two components, mg sin theta and mg cos theta. Mg cos theta will simply balance the normal reaction, and there is no motion along that direction, so it's not going to do anything. We don't have to worry about it. Mg sin theta is the one which will then balance this friction force and the tension in the spring, and because of that we will have some motion. Okay. So we can again start writing down the equation of motion. So let's do that. And if you want to write it down, then we'll have mg sin theta minus f minus t is equal to m1 a1. So m1g sin theta here, right? So this is one equation. Similarly, we will have for the other one. So we'll write it as T minus M2G is equal to M2 A2. This is my second equation. Now let us say that the drum rotates with angular acceleration alpha about its center of mass, right? So we can also write down the torque on this. Now the torque on this is because there is a friction force F here, there is a tension T here on the two ends, and the drum is rotating. So the torque is going to be equal to then F of R, so friction force, and this minus T of R, and this is then equal to I alpha, right? And one can see that since both the forces are in the same direction but on the opposite ends of this of the cylinder or the drum, they are going to produce torque in opposite direction. Okay. Now these are equations. However, we need more, right? Because right now what we have? Right now we have A1, A2, we have alpha, and we have this tension T. So we need more equations to solve for this. Now, what are the equations that we need to solve for this? Is again now the drum is rotating without slipping. So rotation without slipping. Okay. So this is going to give us a relation between A1 and alpha, where A1 is simply alpha R, right? So this is my equation number 4, and I can write down now looking at the constraints of the problem, right? So there is also a constraint of the problem. So in the last example we saw that the constraint was that since the two masses are connected by the same string, then their acceleration have to be same. Now here, of course, the masses are connected by the same string, but there is a motion of the string in the sense that the string winds around this drum, so they can have different accelerations, right? However, because of this rotation without slipping and the drum and this mass being coupled to that string, we'll have a constraint condition which basically will then say that A2, acceleration of this is equal to twice of A1, right? So if this one winds around, let's say 1 turn, then the drum also moves some distance, the rope winds around on this, so this one makes an additional motion compared to the drum, right? So A2 is going to be equal to twice of A1, and then this is my equation number 5. And now with all these equations, we can solve for A1 and A2, right? And as well as alpha. So if we do that, again, it's an exercise for you that with these equation of motions, you find out all the unknown quantities. What we'll get is A2 is m1 sin theta minus 2m2 g over 3 by 4 m1, so mass of the drum, plus the twice the mass of hanging weight. So then we can solve for it, and once we have A2 we can find A1, once we have A1 we can find alpha, and basically all the quantities are then known to us. Okay. So this is another example of solving these kind of problems using, so far we are just using the fixed axis rotation equation of equations, right? Because those are the ones which are applicable to these systems. Let me finish this by considering a problem of something very simple, the simple pendulum, right? However, so let's write it down as example. And instead of a simple pendulum now, right, where you have a spring and and a massive object, but then we normally take the dimension of that object to be null, a physical pendulum. Right. So where we are not bothered with a string and a bob and this kind of system, but we say that take any arbitrary object, right, pivot it at any arbitrary point on that object, right, or about any other point, and then let's see its oscillations, right? Because that is also a motion which is similar to simple harmonic motion. However, we just want to see that is there now any difference between considering the idealized system of a simple pendulum and this kind of realistic system. So this is called a physical pendulum, and basically what I am saying is, let us say there is some arbitrary shape, right, and let's pivot it here. So this is my pivot point, and I have, this is my vertical. So I have displaced it again. I have displaced it by certain angle theta, okay, about this vertical, and it's free to rotate. So it makes some angular oscillations with angular acceleration alpha, and will have some characteristic frequency omega naught and all that. So this is like a simple pendulum, right? A simple pendulum with a spring here, bob here, and then making a motion. And now I want to solve this. However, I am not going to use the force balance and all that. I am simply going to see this as a rotation about a fixed axis, right, which is passing through the mass and perpendicular to the object, and then the perpendicular plane from the perpendicular plane of the motion. So about this axis, I am just going to consider this as a rotational motion and then solve for it. So for that, what we need is, I need to find out which force is providing the torque. So if this is the center of mass and mass of the object is m, then mg acts at this point, right? That this we know, that's how we define the center of mass. And let us say that from the pivot point to this center of mass, we have length L. Right? So we don't care about what is the size of the object and all that. Right now all we need is to find the torque on the system is the total force acting, which is mg downwards, acting as if acted on the center of mass, and distance of this point from the from the pivot point, right? And now the torque is this distance and the perpendicular force. So we'll break this down into two components. The component along the L will simply give centripetal acceleration, right? Will not lead to the rotational motion, and the component perpendicular to it will lead to the torque in the system. So this will be mg sin theta, right? And so we can write down now torque on this is minus mg L sin theta. So minus mg sin theta is the force, L is the perpendicular distance, and this is equal to I alpha, right? It's a fixed axis rotation case, I alpha, right? Okay, very simple. Now all we have to do is write down this alpha in terms of this angle theta, right? So the alpha is basically d2 theta over dt square is equal to minus mgl sin theta, which I can approximate again as minus mgl theta for theta close to 0. So small angle oscillations, we still continue with that approximation, and if that is the case, then I can write down this as the familiar equation of simple harmonic motion, mgl over I theta equal to 0. So this is for a physical pendulum, independent of the shape and other things. All that information is contained here in the moment of inertia. And now if I want to describe it, so we know what is solution, but I am more interested in the frequency. So how the characteristic frequency changes when we move from simple pendulum to a physical pendulum, omega naught, and we know what is omega naught, right? Omega naught is now nothing but mgl over I. So this is the characteristic frequency. So in case of simple pendulum, omega naught we calculated as the square root of g by L or L by g. You can check that. But anyway, we know what is the we know what is the angular frequency in case of a simple pendulum, right? So now this is my natural frequency for a physical pendulum here, right? And now what I can do is we can write it down in a slightly different form. So first of all, this moment of inertia is about this point, right? However, for an arbitrary shaped body, it may not be possible to calculate, or we may not really know what is the moment of inertia about that point. However, we can use the parallel axis theorem to write down this moment of inertia in terms of moment of inertia about the center of mass, which will normally be known for different bodies, and the distance between these two axes. So I can write down I as ICM plus ML square. Okay, and in that sense, then this becomes my natural frequency becomes MGL over ICM plus ML square, where ICM is the moment of inertia about center of mass, and I can define a parameter. I can define a parameter K. So now this is let me write down small k, K square as ICM divided by the mass of the rigid body. Okay. So this again will have dimensions of this will have dimensions of length square. So K is basically some length parameter. And now if in terms of K, if I want to write down my omega, then my omega, this is omega naught. So then my omega naught will simply become GL over K square plus L square. Okay. So this is then the natural frequency of oscillation for a physical pendulum, not a single pendulum. And of course, we can get back the same result for the simple pendulum if we simply put the correct K. So K is ICM over M. In a simple pendulum, this ICM is basically 0 because it's a point particle. So then the K will be 0, and in that case, this is just G over square root of G over L as we wrote it down. This K is defined as or described as radius of gyration of the object, of the rigid body, right? And of course, they are related to the moment of inertia about center of mass and the mass of the object. So, for example, if let's say my physical pendulum is made up of a solid disc, then I know that ICM is half mr square, where r is the radius of the disc, and in that case, K of disc will be half mr square by over m, right? I mean K square. So this will be then 1 over square root of 2 r. Right? And similarly, we can find it for various different objects. Right? So depending on the particular problem. Okay. So this way we have seen how to apply specifically these equations, but basically the framework that we developed for rotational motion. And next we will see how to now couple translational motion, right, where now the axis is making the translation as well as the relation about that axis into this framework.